Hi, this is Yomi Omorewa. Yomi Omorewa is a graduate of chemical engineering and someone who is very passionate about teaching. And as a result of that, I decided to go into education as well. I take math, physics, chemistry, and further math. That's my core subjects. Of course, there are other subjects I take, but these are my core subjects. So you're welcome to my YouTube channel, and I will be looking at this now, physics, and the topic today is gravitational field. Gravitational field. Okay, so it's important we define what a field is. Okay, we know that a field has to do with a region or a space under the influence of some physical agencies, and those agencies could be your gravitational force, your magnetic force, your electrostatic force, as the case may be. So that's a field right there. We have what we call the scalar field, and then we have what we call the vector field. Okay, the scalar field and the vector field. So just as you learned in your school that we have vector quantity and scalar quantities, so you were told that vectors quantity are those that have magnitude. Not only that, they also have direction, but for scalar they have just magnitude and no direction. Example of that, you have your time is a scalar, you have your mass is a scalar, your speed is a scalar, your temperature is a scalar, and so on and so forth. All these are scalar. And then you talk about your vector field. For example, your displacement, unlike your distance, which is a scalar, displacement is what? Is vector, because it has to do with distance moved in a specified direction. And your velocity is also a vector, your acceleration is a vector, your force is a vector, your momentum is a vector, and so on and so forth. So understand the difference between a scalar field and a vector field. So for a vector field, we know that it involves direction, it involves magnitude as well, but this does not involve direction. Okay, so now we know quite well that we're talking about gravitational field, and I did say that a field is is under the influence of some agencies, and one of those agencies is what we are considering even now, and that's the gravitational field. Okay, it means that a gravitational field therefore will not be a kind of field under the influence of gravitational force. Let's put it that way. And of course, you know that you cannot feel the impact of a gravitational force without the presence of a mass, just as you cannot feel the presence of an electric field without a charge, or just like you cannot feel the presence of a magnetic field without the presence of a magnet. So you cannot feel the presence of a gravitational force without the presence of a mass. Okay, so that takes us to Newton's gravitational law. There's a law called the Newton's gravitational law, and this is what the law says. This is what the law represents mathematically. So it says that the force, okay, the force is directly proportional to the product of masses m1 and m2, and this same force is inversely proportional to the square of their distance. So this out there is not radius, but it's distance. Please take note of that. So it means that our force is directly proportional to mass. So sometimes this could be moon, this could be earth, depending on what you are told to find. And then our force is inversely proportional to our distance, the square of the distance. Okay, that's what we're saying, the square of the distance. Now, if you are to change the proportionality sign, then you introduce what we call the gravitational constant. Okay, so to do that, you have the F is equals to G M, let me use capital M and small m, over r square, where this is your gravitational constant. Your what? Your gravitational constant. The value is actually 6.67 times 10 raised to power what? 11. If you make it subject of formula, you have Newton meter square over kilogram square. Okay, that is if you make G subject of formula. And this is an experimental value, is a constant, so take note of the constant value there. So when you are given a question, the question will say that you should find the force of attraction between the masses M1 and M2. You'll be given this is already a constant. You'll be given M1. Sometimes the masses, the value of the mass might be the same for both. Sometimes it could be different. Maybe you are told the mass in the of the mass of the moon and mass of the earth and all of that, and then you are told the state of the two masses. The value will be given to you. You substitute it here, and then your radius, your distance rather, is in meter. And so sometimes they may give you in centimeter, you divide, or they give you in millimeter, you also divide, knowing fully well that 1 meter is equals to 100 centimeter, or 1 meter is equals to 1000 millimeter. Okay, so depending on what you are given, you make sure that you divide appropriately to the standard unit meter. And if they give you in kilometer, you could also make sure, knowing fully well that 1 kilometer is 1000 what meter. So you do your appropriate conversion, and then you make sure you solve. I'm sure that's very simple. So the next thing we want to look at is how we can relate the capital G, which is the gravitational constant, and a small g called acceleration due to gravity. Is there a relationship? Yes, there's a relationship, and you can be asked to solve, or you can be asked to find something. Maybe a question is given, and then you are told to find the acceleration due to gravity. Of course, we know that it has a constant value, 9.81 or so meter per second square. Okay, but then is there a relationship between it and the capital G? Let's say, and as we go on, so we have, so we start by saying the relationship between the small g and the capital G. So what that means is that your small g is F over m. What does this mean? It means that acceleration due to gravity, or what you call, there's what we call electric field intensity, or what we call electric field strength. Okay, you will understand that. Just make sure you follow on the YouTube, my YouTube channel. We can also call this gravitational strength. Yes, I can call it that way. I can call it gravitational strength. Yes, I can call it that way. So now, so in that case, what is my F? My F is there on the board, which is my what? My capital G, my big M and small m, you could put it that way, over my R square. You can see the division line here. So division, and then we have our N. So that my G is equals to this over what? R square multiply by what? By 1 over m. So this goes up. This you change it when it's division. So that's what I did here, because this is what we're having before. And if you change it to multiplication, you take it up there. So this cancel the. Therefore, you have your small g equals to your big G, your n, over what? Your R square. You can see the relationship here. And I could make m subject of formula. If I make m subject of formula, I'm going to have, in case you are asked to find, so you have something like this over what? The capital G. So this is it. And do not forget what is happening here. Sometimes the radius can become the radius of the earth. Yes, you can be given the radius that R. Instead of in distance now, it can become radius of the earth. And you know the radius of the earth is 6,400 kilometer, and sometimes they don't give you in this way, so it becomes 6,400 kilometers, 6.4 times 10 raised to power 6 meter. What that means is that it's been converted to meter, and you know that 1 kilometer equals to 1,000 meter. So when you are given question, remember, the question can say you find this, the question can say you find, you could decide to make any of them the subject or formula, and you're good to go. It's simple and it's straightforward. I'm sure that's very clear. If you have any question on what I've just demonstrated, you can drop it in the comment section, and there will be a continuation on this another time. Bye.